Hello, everybody. Welcome to this scientific workshop organized by INRAE and RobAgri. It's a second workshop we are organizing within FIRA. 2020. I am Roland Lenin. I am a researcher in INRAE and president of the scientific committee of RobAgri. And I will moderate this session with Stéphane Durand, which is the project developer at RobAgri. So before starting the scientific talks, we just have a brief short presentations of RobAgri associations. So the objective of RobAgri is to bring to the market robotic solution for agriculture and to permit ecological transition of agricultures. And if we want to have robots that are able to do that, we have to solve some operational challenge, which has also some needs in scientific issues to be solved. And then the idea of the associations is to bring researchers, engineers, private company, public laboratory, farmers together in order to permit to accelerate the development of these new technologies. So RobAgri try to put together new developments, new infrastructures, shared development tools, and to think together about standards, testing procedures for robots. Our association is now composed of 71 partners, which are dispatched into several kinds of institutions. So we have robot manufacturers, machine manufacturers, tractorists. We have suppliers, we have public research laboratories and schools, and we have also end-user representative and robotics in agriculture representative and farmers representative. So from a scientific point of view, what we actually do is that we identify scientific issues, main development we have to do together in order to find new solutions. And for this purpose, we organize a scientific workshop. We are trying to put together an algorithm database and also dataset database in order to have the same background. And we are also writing some scientific books and proceedings in order to help people developing their own robots. We have also some action from a technological point of view regarding safety analysis, sharing testing infrastructure and developing new testing infrastructure and evaluation processes in order to check efficiency of robots and safety of robots. And to do that, we have main actions. We are involved in the DIH agro-food that you can see on the FIRA. We are involved in a French project funded by the French Ministry of Agriculture, which is RobAgri, which is just finished. And we are trying to deposit some answers to open call in order to have shared and common equipments and also virtual equipments. From a scientific point of view, we gather in France 15 main laboratories working on robotics and especially in off-road robotics in several kind of areas, and we are trying to cover all the thematics of the disciplinary that are needed in order to develop new and efficient robots. So now I let Stéphane talk about other actions we are leading in RobAgri.
So thank you, Roland. Roland, which is the president of the scientific committee of RobAgri. I'm Stéphane, and also a project manager of the association. So what is different about our association, or particular, is that we represent a great variety of actors, and in order to better represent the sector, as you saw, Roland told you, we've got laboratories, industrial startups and also farmers. We've got 5 axes to do this. The first one is the norms, is working on norms and safety. And we did a strong work on this when we started 3 years ago. We also got many actions on technology transfer, as Roland told you, from research to industry. We also focus on the future farmers' needs because with climate change, robotics will be one part of the answer. And we have to adapt to farmers' needs and to the way farmers grow and will grow their crops in the future. Also, a 4th axis, Roland told, which is about testing and assessing machine performances, because farmers want to know if the robot will be able to do its task. And then one real important task, which is the 5th one, is to represent the sector about the authorities and the French state. And I want to thank you, French Minister of Agriculture, Mr. de Normandie, for coaching our association, as well as INRAE, yesterday during his speech at the FIRA. We can go to the second slide, and the main message I want to tell you is that about the association, about what we do, is that the more diverse you are, and the better you represent the sector, and the more efficiently you tackle technology challenges, and that's what we try to do. These are the 2 main axes of our association. So some example of what we did some common guidelines for risk analysis for industrial and startups, robot makers. We did some common work on machinery directive with AXEMA in link with SEMA at the European level. We also did a proposal to the French state to get a regulatory regulation to test on-road crossing for robots in manual mode in rural areas. Also, we work, as I told you, with farmers in order to see their needs and think about their future needs in order to adapt robots. Then last May, we did a strong report. We made 10 proposals for the robotics sector to the French state, ranging from research to market, and all our 71 members were associated to this document. Our next challenges, in fact, we should go on cyber security, future farmers' needs, also, as Roland told you, ROS and database algorithm, and also some interesting topics about GNSS positioning. Last, I want to welcome you to this scientific forum, and also on behalf of the board of the association, invite you after the forum on our site, in fact, stand on the FIRA. You will be able to meet Jean-Michel Lebars, which is RobAgri president from Kuhn machinery, agricultural machinery company. You also got Xavier Robou, which is from INRAE, RobAgri's vice president. And I want to thank you, INRAE, for supporting us since we started. Also, François Carpentier, which is a vice president from a cooperative, Ceresia, in east of France. Vitibot, robot makers for vineyards. Dominique Bache, as well as myself understand. So have a good, enjoy this talk, and thank you.
Okay, thank you, Stefan. You can find us on both booths at RobAgri booth and INRAE booth, and you will see also the summary of the different talks we will have today for the second session, which is devoted to human-robot interactions and how robots for agriculture can work with human. And so we have 3 talks this morning, and we start with David Rose from University of Reading and Lincoln, who will talk about toward the responsible development of autonomous robotics in agriculture, a call to action. So please, David, you can go ahead, and I let you present your talk. So just forgot to mention, do not hesitate to ask questions in the Ask Question tabs you have on the audience site.
Great. Thank you very much, Roland. I'm assuming everyone can see my slide now because I've clicked on it. So I'm hoping everyone can see me. If not, I'm sure someone will contact me. So good morning, everyone. Thanks for accepting this talk today. So I'm from the University of Reading. Great. At University of Reading, my group looks at issues like technology adoption and behavior change and the ethics of new technology. And we particularly think about how we can include people in a multi-actor approach to think about how we get to responsible technology futures. And I think it was great yesterday, and I'm sure today, there'll be lots of talk about including people in developing robotics responsibly. There were lots of sessions yesterday saying we need to ask consumers, we need to include farmers, we need to include farm workers, which was great. But there wasn't that much detail about the different methods that we could use to do that inclusion and to help anticipate futures. So I'm going to present a few possible methods today, which hopefully will ensure that we can go away and have a think about, whether we could do inclusion and anticipation better. So the challenges in the soft fruit industry, which is particularly the sector we're working in at the moment, is well versed. You'll all know it's not limited to soft fruit, but you'll all know the challenges faced by many growers about lack of labour due to COVID and lots of other issues in the UK. Brexit has been a problem in getting the labour that's needed. And that's a huge problem for the UK soft fruit industry, which is worth about £450 million at the farm gate. It's worth about £1.5 billion in retail. If there is no solution to this lack of labour, then this fruit won't get picked, and that presents challenges for the environment and for food security and for the sustainability of farm businesses. So we're involved in an Innovate UK funded project with Saga Robotics, Thorvald, who are leading the project, very much driven too by the University of Lincoln. They're one of the leaders in the UK in terms of agri-robotics. They've got a huge centre where they do this work and a huge centre for doctoral training. They have many different PhD students a year looking at autonomous robotics, also supported by industry. So Berry Gardens is a leading UK berry and soft stone fruit production and marketing company. And then we've also got some support from the Manufacturing Technology Centre and BT. And this is a 3-year project, and it's going to be the largest known global demonstration of robotics and autonomous systems that fuse multiple technologies across a single farming system. So the idea from this year and also through to next year is we demonstrate a number of different autonomous technologies with the hope of, before too long, putting them all together that will do fruit detection and forecasting, UVC disease control and crop spraying, fruit picking, logistics support of the picker, pack house integration, really to automate almost every process that goes on a farm. And we've got a trial site in the southeast of England where we're doing this. So the robot, I did have some videos to play, but I didn't supply a video file, which was my fault. So you'll have to imagine it. But essentially the robot that we're using, that Saga Robotics have designed, is a modular mobile platform. So it's a base, so you can strap various things to it. And there can be multiple of these robots on the farm at the same time doing different things. So the idea from this summer, because the need in the soft fruit industry is so strong, that we will start to demonstrate some of these technologies, look at the economic benefits, but also our job, which is at the University of Reading, which is to think about how we include end user voices in the design and the demonstration of these robots. Because as was said in one or two sessions yesterday, and I'm sure will be reflected on today, a lot of new technologies with agriculture, the fourth agricultural revolution, agriculture 4.0, are very exciting, but at the same time, they could also be very scary. We wrote about this in a recent article in The Conversation, that there are many benefits offered by autonomous technologies, and indeed there might be a few other solutions to this labour problem. But there are a number of potential social and ethical and legal issues that are presented by using autonomous technologies on a farm that have the potential to derail the adoption and implementation of these technologies, as we've seen in the past with other technologies in some places like GM, etc. So we've wrote a little paper looking at the different ways in which we can move towards responsible development and implementation of these technologies, and what methods we can use to make sure it is responsible. Because as you know, this isn't surprising to you, almost every potential benefit of autonomous technology could have a downside too, from the difficulty of regulating farm environments, the challenges of data ownership and privacy, lots of potential benefits to employment, attracting younger workers, increasing skilled jobs, losing dull, difficult and dangerous jobs, but potentially leading to some farm workers losing jobs. Economics, potentially providing lots of economic benefits, but perhaps some growers who can't invest may be left behind. Equally for trust and health and safety, that robots could help with data transparency, but they could also not be trusted by the user because of cybersecurity or other safety concerns. They may well provide both sustainability and environmental and social and cultural benefits, but again, there's potential downsides as well of using autonomous robotics. And these are really the issues that we need to get ahead of before these technologies are implemented on farms. So many of these technologies are approaching higher technology readiness levels. Many are being demonstrated. Many of these technologies are not widespread, but are on farm environments now. If we don't get ahead with trying to think about some of these societal and ethical issues and do something about them and change our design and demonstration culture, then there are potential issues that could slow down the adoption, which is not what we want if we want to address very short-term challenges like labour, but also meet targets such as net zero by 2040 or whenever. So we have to, on the one hand, think about how adoption of autonomous technologies can be speeded up, because we know adoption of technology can be slow in agriculture, but at the same time, it needs to be done in a responsible way. And if it's not, that could slow things down. So many of you will be familiar with the responsible innovation concept. It's widely used now. In the EU Commission use it for Horizon 2020 calls, etc. So there's four different components of responsible innovation. So one is anticipating the potential consequences of an innovation, both good and bad, and the easy to foresee and the hard to foresee, to think about the consequences of your technology. Reflexivity, to think, okay, once you get some feedback from users, do you actually incorporate it into your design and delivery? If you don't, if you're not open to change, you're not being reflexive. Thinking about inclusion, so are we actually including all the affected stakeholders and actors from start to finish in the design and the delivery process? And then lastly, responsiveness. So do we have sort of laws and policies, regulations that keep up to speed with the development of the technology and can be an enabler to its use, but also prevent problems occurring from its use? And I think we can see this concept being used in lots of settings now. So in the UK, the British Standards Institute produced this responsible innovation guide for our big research funder, Innovate UK, that funds a lot of this work. We've seen responsible innovation type principles I think, be embedded into a code of practice for autonomous machines has been developed in Australia, which I'll talk a bit about later on. So there are bits of responsible innovation going on in autonomous robotics in agriculture. There's a lot of particularly anticipation going on, thinking about what the future looks like, what the problems are, and a little bit of sort of responsiveness, thinking, well, what do we do about that in our institutions and policies? But I think more could be done. So if I go through each of these briefly, this is more just to think about what might be possible, thinking how we're doing responsible innovation at the moment and maybe how it can be improved. So in terms of anticipating the consequences of autonomous robots in agriculture, there's been a few common methods used. So, by far the most common is to do a sort of farmer or consumer survey where you ask them what their concerns are. Do they have safety concerns? Do they have cybersecurity concerns? What do they think of using robots? That's a very common method. There are others, such as Wizard of Oz studies, where you might simulate autonomous capabilities. So you might have someone actually operating them by remote control, but the farmer or the farm worker in that environment doesn't know it's being remote controlled, and you can try and gauge their reaction to it. You could do various foresighting exercises where you try and think about problems that will happen in the future. Science fiction approaches and horizon scanning might do something similar. There's also methods such as backcasting, so you can think about a desirable future state, which might be the safe use of robotics in agriculture, and then work backwards to think about the steps that you need to put in place to get to that future. There's lots of different methods, but I think we too often just do a farmer survey or a consumer survey and almost ask if they will accept the technology, which doesn't really allow, deep anticipation of potential consequences. So I think we could use much more, much deeper methods to think about how we anticipate the future. The second one, and I think this is the most important, and there was lots of talk about this yesterday. So I think in the very first talk in the scientific workshop, Christian talked about roboticists or almost needing to be social scientists as well, to know how to include all the different actors and stakeholders in the design and delivery of autonomous robots. And I think we need to be careful what we mean by multi-actor, and to ensure that we are including all of the stakeholders that are affected by autonomous farm robots. So it's okay asking the growers what they think, but what about the farm workers who have to work alongside these robots or might find that their jobs or tasks are replaced by these robots? What about consumers, about what they think about consuming food that's been produced in this way? What about farm advisors who might see their role change? There's lots of people who are involved in both food production and consumption that you would think have a stake in the use of, in food production systems. So I think we certainly need to get better at including a wider range of people in design and implementation of these robots. So I think we need to test different methods of inclusion. I think, again, we rely on surveys and the odd workshop too much. There's some evidence, some studies of field-based observation where robots have been tried in the field alongside workers, and you ask them what they think. But because many of these technologies aren't implemented on the ground, and there are legal challenges, legal issues in being able to use these and conduct studies where these things are working alongside people, there are some limitations so far in how we've included, because if you're not demonstrating the technology for people to actually see how it works, it's kind of difficult for people to understand actually what this technology is and how it works. If you just do a survey and ask growers and farm workers and the public what they think, but you don't include enough information or demonstrations, of how they work, it's kind of hard for them to give informed answers. So we might think about how we do that better. The last two components, which I think are perhaps equally important, is I'd invite everybody to think when we have included users, if we have included users in the design of our robots and in the delivery, how reflexive have we been? So without wishing to be too complicated, and I know social scientists can be very complicated, we talk sometimes of two orders of reflexivity, first order and second order. So the first order, I think, is very much what we tend to do, which means we ask users what they think of robot safety features or cybersecurity features, etc. And based on their feedback, we tweak a bit of the design. So we put an extra safety feature on the robot, for example. And this is good. We should definitely carry on doing this, asking users what they think of the robot and incorporating their views into the design process. Of course we do. We need to do that. But we rarely do a sort of deeper form of reflexivity where we maybe question some of the underlying assumptions and consider alternatives. And that can lead to using a sort of public acceptability lens where we just are hoping that people are going to say yes and we'll do everything we can in order to make users accept this, which some would argue is a bit more a rather narrow approach. But I think we certainly, as roboticists, scientists, all of us need to try and be a bit more reflexive in public. And when we've included users in the design and delivery process, we need to tell them more and show them how we have incorporated their views and done something different based on what they've told us. And just lastly, before I finish, this is a key question, I think, for this conference, and will take lots of thinking as we move forward. But there needs to be laws and regulations and standards and institutional structures that allow the safe and productive use of these technologies in the field. And I think the best example of this so far, where a code of practice has been drawn up, is the Australian example. We know there are lots of international standards that either do already relate to agricultural machines or could be used to inform the use of autonomous equipment in field farm environments, although there's more work to do here. But we need to think about what is the best sort of toolbox of laws and regulations and standards and codes of practice that we need in order to ensure that these things, autonomous robots can be encouraged if that's what society wants to be used, but it can be done in a safe way. And I think sometimes the law is not good, obviously, at keeping up with new technologies. It's very reactive. But I think as roboticists, we need to think, anticipate what some of the legal issues are going to be in the future. And that will mean working with others and thinking about how we can almost head that off by working with standards institutions and policymakers to have systems in place before those things are implemented. Because the last thing we want, and you can see this with the autonomous vehicles, driverless cars, Uber, etc. The last thing you want is these technologies being used in a sort of political and legal system that isn't strong enough to ensure its safe use. And then we have some sort of absolute disaster where a robot runs someone over or chops someone's arms off. And that will lead, that could set the whole project back a number of years. So we really do need to think about not rushing all of this and thinking about how the environment is going to be safe. So the next step for robot highways, we're going to try and take some of the things we've learned from the literature review that we've written in this paper to think about before we demonstrate these technologies in the summer and for the next 2 years, how are we going to include growers and workers and even consumers in this process? Once we've consulted them, what are we going to do to change our design process and our demonstration process? And so there's much more empirical work we need to do, and I don't think we have many answers at the moment. But I hope this talk has inspired you a little bit. I know it's sort of complicated social science in many ways, just to think, if we're serious about doing responsible design, and I think that is absolutely key to avoid controversies about this technology, what methods do we need to use in order to make sure that design and delivery is responsible? And there's no one way to do it, but hopefully I've inspired you to at least go out and do some reading and work with others to think about how we can do this more effectively in a multi-actor way. So if there's any questions, that's my email, that's my Twitter. Thanks particularly to all the collaborators, particularly Lincoln and for this talk, but also Saga Robotics, Berry Garden Growers, MTC, BT and Clockhouse Farm, and INRAE for the funding. So thanks very much.
Thank you, David. Maybe we have time for one short questions. And there is questions in the chat, and do not hesitate to ask questions. What do you think about the Australian Code of Standards? And somebody viewed that they want to make the end user responsible of the safety assessments. And do you see the same thing in UK?
So there is a similar process going on in the UK. So we work with Harper Adams University. Many of you will know Harper Adams through their hands-free hectare and hands-free farm project. So they recently led a workshop to think about whether we need a similar code of practice in the UK. And we had the Australian person that led the Australian version come and speak to us. And it was a very interesting process that they used. They managed to do it all through COVID lockdown. They did lots of Zoom workshops with industry and some growers and developed that code of practice. And I would invite you to, I think it may well be publicly available. If it's not, you'll be able to ask. His name is Rohan Rainbow for a copy. I think it's still in consultation, but it'll be out soon. One thing I think there is work to do to make it more inclusive. So and I think this was partially as a response to COVID. There was limited inclusion of growers and workers and consumers and other people of society in developing that code of practice. And one could argue, if you don't take an inclusive approach to a code of practice, what legitimacy does it have when you come up with it if, farm workers, for example, haven't had an input into it, etc. So I think there are probably things we can do to improve upon it, but it represents, I think, one of the first really nice bits of work that have tried to develop a code of practice. And I think it very much inspires other people to think about doing the same for their countries and regions.
Okay, thank you very much for your answer. You have now some questions in question tabs. So David is able to answer during the next of the sessions to these questions. And do not hesitate to keep on asking questions on David. Thank you very much.
Thank you.
And time is running, so it's time to switch to the second talk of these sessions, which is given by Yoshikazu Kusumi and Fumiaki Kudoh. Sorry for my bad Japanese pronunciation. And I don't know if it's fixed right now, but we had some issue with this presentation. So you have a tab in order to follow the presentations, which is called Event Resource Tabs, and you can have access to the presentations of Fumiaki and Yoshikazu using these tabs, following the PDF, and maybe Fumiaki and Yoshikazu can tell us which slide they are talking about when they talk. So please go ahead.
Okay. Can you hear me? And can you see me?
We can hear you.
Can you hear me?
Yes.
Can you see me? Oh, okay. Thank you, moderator. And please let me announce again. Due to system trouble, today we can't show our presentation slides on this virtual conference application. So all participants, please check the Event Resources tab. It's located at the below of this page. You can find our PDF file. So it's our presentation slides. So please download and read it. And I explain about it from now. So let's start the presentation. Wait a moment. Sorry, at first the presenter was changed to Yoshikazu Kusumi changed to Takuya Murayama. I'm Takuya Murayama. I'm in charge of research and planning at NTT Corporation. Thank you for giving us this opportunity. In this presentation, we will be introducing cutting-edge technologies that will be necessary for the future of agriculture. One of them is the technology needed for field-to-field self-driving and remote monitoring and control of robotic agriculture machinery. And the second is about security technology for smart agriculture. Then I explain about page 1. This is an outline of NTT Group. Originally, NTT was a public corporation in Japan. NTT Group is a leading company in the telecommunication business. We operate in a wide range of domestic and overseas markets by utilizing the customer base and expertise in communication networks and ICT. NTT is a holding company and promotes basic research and development. NTT Group corporations are doing regional communications business, long distance and international communications business, mobile communications business, data communications business, and so on. Then I explain about page 2. We set a strategic field while group businesses push forward various actions. We place the agriculture with a future growth area, and such group companies push forward various actions. Go to the next page, at page 3. So today, I'd like to share with you NTT's research and development efforts in the agriculture sector. There are 2 topics. The first is remote monitoring and control of automatic agriculture machinery. And the second is security for smart agriculture. I go to page 4. In this part of my presentation, I'd like to tell you about the background of our research. Japanese agricultural industry has been facing a labor shortage due to the long-term decline in the number of farmers and the aging population. Additionally, the spread of COVID-19 this year has caused the number of foreign technical interns to decrease, and the agricultural workforce is shrinking more quickly. On the other hand, the world population has been growing, which may lead to worldwide food shortage unless agricultural productivity is improved. Go to next page, page 5. Now, to compensate for the labor shortage, farmers are expanding their work area. However, manpower is limited, and it will be difficult to make up for the continuing labor shortage in the future. Please go to the next page, page 6. In order to maintain and expand agriculture, it is required to work in increasing work areas due to labor shortage without relying on human labor. The maximum possible automation of agriculture work through the use of robotic agriculture machinery is also expected to resolve the labor shortage we are facing. I go to the next page, page 7. Therefore, we are working on research and development for the realization of automated farming with robotic agriculture machines. And this is an overview of the experimental system. On the left is a picture of a robotic farm machine performing automated farming. Based on the signals received from satellites, the robot farm machines provide highly accurate positioning and automatic driving. These robotic farm machines are equipped with cameras. The high-resolution images from the cameras are transmitted in real time to a remote monitoring center using the latest 5G network. The picture on the right shows the surveillance video at the remote monitoring center. The upper image is the front view of the robot farm machine, and the lower image is the rear view. We can check the presence or absence of hazards around the farm machine and the results of the work. If a problem occurs, the robot farm machine can be stopped by remote control from the center. The goal is to dramatically improve the efficiency of agriculture by enabling a person to remotely monitor and control the work of multiple robotic farm machines at once. Then please go to the next page, at page 8. This year, we have carried out research, development, and experimentation in technology to further advance the automatic running and remote monitoring and control of robotic agriculture machines. One is network technology that enables stable and smooth automatic driving and remote monitoring, even over large areas. The other is positioning technology that allows highly accurate positioning even in environments where it is difficult to receive satellite signals directly, such as a field near a forest. In this presentation, we will introduce our flagship technology, a multiple network quality prediction technology. So go to the next page, page 9. In order to achieve fully automated work with a robotic farm machine, the robot farm machine must be able to move between fields. Thus, in sparsely populated rural areas, it is assumed that public roads are covered by 5G, but farms have to be covered by a private network. In such cases, there are challenges such as the difficulty in implementing continuous and stable remote monitoring. The one solution is to predict multiple network quality and switch networks before the network becomes unavailable. We have been using AI to predict fluctuations in communication quality. It enables automatic switching to the appropriate network before the communication quality deteriorates. And even if it is necessary to switch networks when the vehicle is running automatically, it does not interrupt the remote monitoring. We prepared a video of the experiment, so please watch the video. Wait a moment. So video. Now the video works. We did an experiment last month, November 2020 in Hokkaido, Japan. We used the Kudoh robot farm machine for the experiment. The robot farm machine is equipped with cameras, and this way it can be remotely monitored. Our technology can thus automatically predict the quality change of different networks and switch to the optimal network like this. This shows the throughput of video communication. You can see that the communication is smoothly switched from BWA to 5G. It's the experiment. Then we back to the presentation document. Please look at the page 11. In the future, NTT, sorry, we have to stop the video. We go. Okay. Sorry. In the future, NTT aims to create a new high bandwidth, low latency network in addition to technologies introduced here. This will enable the efficient remote monitoring and control of hundreds of robotic farm machines, resulting in an overwhelming reduction in the labor force. In a world where hundreds of robots move around automatically like this, the control of these robots must not be taken away by outsiders. In the next session, Mr. Kudoh will discuss the security technology to prevent these risks. Please explain, Mr. Kudoh.
Okay, thank you, Takuya. I'm Fumiaki Kudoh from NTT, and from here, page 11, I will talk about the security technology required for smart agriculture. We think that some security threats will increase as self-driving and automatic cultivation will become more widespread, like we have talked about so far. Therefore, move to next page, page 12. In the latter part of our presentation, we will introduce our lightweight authentication technology for IoT. We believe our technology can enable secure IoT in smart agriculture. Move to next page, page 13. This is the image of the future smart agriculture. Sensors, control devices, and self-driving machineries will exchange various information and control signals by various networks for automatic control. If the information exchanged by these devices become variable, it can be targeted by attackers. Now, this time, we will talk about how security threats exist in smart agriculture. Using the demonstration experiment of automatic tomato cultivation system that we are currently conducting as an example. Please move to the next page. This is a system overview of our demonstration experiment to grow tomato automatically. Sensors on the field constantly send environmental information such as temperature, humidity, and illuminance to cloud server. Based on this collected information, AI on the cloud server determines the optimum irrigation timing. It means watering timing, and sends the irrigation command to the control equipment. Please next page. We think that there are several security threats to such automatic cultivation system. For example, leakage of valuable cultivation know-how and disturbance of cultivation due to unauthorized operation. So security technology such as encryption and mutual authentication that protects communication data is required to protect variable cultivation know-how and to build a safe automatic cultivation systems. Please next page, page 17. Next, let's talk about traditional IoT security. The IoT communication environment is different from the general internet. First, IoT devices generally have low power CPU and memory performance than PCs and smartphones. So technologies with high calculation cost cannot be used. And second, depending on the farm, carrier networks such as 4G and 5G may not be available. In such cases, narrowband networks such as LPWA, for example, Sigfox or LoRa, are often used. Therefore, it is necessary to consider that it can be used even if the communication speed is slow. In other words, public key infrastructure such as digital certificates, which are commonly used on the internet today, cannot be used on the IoT for smart agriculture. This is because an amount of communication of PKI is too large to use with LPWA. Please, next page. Next, so how is data protected in today's IoT? Many systems use fixed password or symmetric key cryptography. However, data protection using these technologies is not sufficient, we think. This is because many devices shipped from the same factory often use the same password and key, and the extent of damage when this confidential information is leaked becomes extremely large. Public key-based cryptography is absolutely necessary to provide data protection that is resistant to key leakage. Go on next page, page 19. Therefore, today we propose a lightweight and secure authentication technology based on public key cryptography for IoT. Our encryption and mutual authentication technology uses ID-based cryptography. That is a type of public key cryptography, and we have succeeded in significantly reducing the number of calculations called pairing compared to the traditional method of ID-based cryptography while maintaining safety. Go on next page, page 20. As you know, this is a core protocol of our technology called authenticated key exchange using ID-based cryptography. However, this is a little difficult to explain. So please see next page, page 21. Here is a slightly simplified overview of our protocol. Each entity is issued by a key generation center or KGC, its own private key and ID as public key in advance. Then, when starting a session with the other party, ephemeral public key is generated and notified to each other. Using this information, a shared key is generated by a pairing operation. If the communication partner is correct partner, the same shared key will be generated. So mutual authentication is performed by confirming that the same shared key has been generated. And encrypted communication can also be performed using this shared key. This is overview of our technology. And go to next page, page 22. Finally, I'd like to explain the features of our technology once again. The advantage of our technology is that it has significantly less the amount of communication than PKI. Also, the calculation cost is not large. Due to these characteristics, it is very suitable for use in narrowband network and powerless IoT devices. Go on next page. Well, this is conclusion. Our lightweight authentication technology enables secure IoT in smart agriculture. And we plan to make it a service as a platform of the entity group. Thank you very much.
Thank you very much, Fumiaki. We have time for a short question. There is a question from the other audience, which is, you have settled your system in a real experiment. How many systems have you installed, have you settled in Japan?
Okay, yes. Thank you very much for questions. But actually, we have not yet installed the real field. Now we have verified the application we have verified the application to IoT devices and some control equipment. So it's just a demonstration experiment yet.
Okay. And do you manage also the fact that an antenna can break, or how you are able to reconfigure the network?
Sorry, you were breaking up. Sorry.
In the presentations, you mentioned that you can see the different antennas, the different beacons that you use in order to preserve the communications. If there is a failure in the one antenna or a broken antenna because of the weather or something like that, do you can you reconfigure the network, the remote network?
Okay. Our security technology has the advantage that it can be used in any network, even if it is a narrow band. And our technology can be used from narrow band network to wide band network. For example, our technology can be used LPWA or 4G and 5G. In any networks, okay, our technology.
Okay.
Sorry, does that answer your questions?
Yes, approximately. But I will talk. I will ask my questions on the board, so there's no problem. Thank you very much.
Sorry.
You're welcome. Thank you very much. Time is running, so we have to switch to the third presentations, which will be made by Benjamin Kisliuk. Sorry. Kisliuk, which is not from the B2FEI, but from the German Center for Artificial Intelligence.
Yeah, thanks. Hello everybody. I hope you can see me, and I hope you can see my slides. Thanks for the introduction. My name is Benjamin Kisliuk. I'm from the German Center for Research Center for Artificial Intelligence, from the group of plan-based robot control. We do a lot of works in agriculture for quite some years now, and we focus mainly on sensor data interpretation and long-term autonomy in robotic applications. And today I want to present to you and, if you like, discuss with you about a new approach towards robot navigation on agricultural, on agricultural sites in agricultural environments. So our motivation, I suppose, is the same as for many with you. We see that agriculture is already a huge driver for innovation, and so for our high-tech applications and research, a very good ground to find applications for robotics and artificial intelligence. The motivation for our current work in context-aware navigation or context sensitivity is that we found that real agricultural sites, like farms, especially in the area of Germany, but I think all over Europe mostly, are probably due to the historic development of the land, of the countryside, very heterogeneous, unstructured environments for machinery and especially high-tech machinery like robots to work in contrast to, for example, factory sites or highly structured environments like office buildings or homes, where we find most robotic applications in practice today. So, for example, when being on a farm, the robot has to be, or a truly autonomous flexible robot has to be able to handle different contexts, for example, for navigation and overall robot behavior. And we wish to further that robots be able to do that. When we work with robots, we mainly focus ourselves on the ROS ecosystem. Many of you probably are familiar with. And we are in a situation nowadays that there are a lot of available technologies we can build our system stacks onto. Especially, there's some kind of default or standard stack many people use in their systems, especially for, I'd say, mainly solved issues, or at least issues where many solutions already exist, like navigation, localization, control architecture, and even environment modeling. So we use a lot of those well-known technologies and want to integrate them in our robot. Here we can see our experimental setup. This is a container we use as a supply station on a test site. We are lucky to have, in collaboration with a local farmer in the Zukunftslabor, it's called Future Lab for Agriculture. It's a project of the state of Niedersachsen, of Lower Saxony. And we see here our robotic test platform, AROX, Autonomous Robotic Experimental Platform. And what we essentially do is that we stick our supply station and the robotic platform with a lot of sensors and tools to be able to test navigation algorithms and operating a robot on a farm. So the robot system itself is not able to perform any specific agricultural processes. This has no implements, but it acts as a sensor platform and testing platform for behavior. What we found is here you can see a drone image of our test site. And what you can already see is that the areas are very differently in usage and also in their parameters, which are relevant for the robot. So on the in the northwest, we see a field which is barren at the time of the picture. More far to the south, there is corn growing. This is perhaps a bit difficult to see, so you have to believe me. There's corn like 1 meter and 50 centimeters high. And on the right, we have a grass area where horses are kept most of the time. Below that, there is, I think, a poultry area. We see buildings which are used for machinery, for animals, but also for living. Because on this farm, in this traditional farm, there is the farmer's family living also. And in the north, you can see a public road. And each of those zones and areas I just described means a very different context for a robot to operate onto or in. Or maybe even be forbidden at times. Like it could be that we might not want to intimidate the animals, so we don't want the robot to drive into the area where animals kept at all, or we are for legal reasons not allowed to drive onto the public road at any time, although it is very practicable to do that because it's a very nice surface for our robot to drive on. But we are not allowed to do so, perhaps for legal reasons. So what we do is, or what we found, is that there are many good algorithms and representations which can be used to drive in each or any of these contexts. But there is no single solution to be able to operate in every one of those contexts at the same time or sequentially. So in current applications, there are various workarounds which come a bit hacky at times. Sometimes they're a bit better or more elegantly solutions solved. But all in all, we see that there are many very good solutions for isolated contexts, but very few solutions on even less good and elegant solutions, which can reliably integrate different contexts on the same application, on the same robotic platform. So what we do is we add an abstract layer of topology onto the classical two-layer navigation stack. So many of you familiar with ROS and ROS navigation in robots probably know the typical dichotomy between a global map and a local map, and we add topological layer on top of that to differentiate the zones we have on the farming side. So, for example, we can differentiate between crop type or plant type, because not every robot might be able, and not every implement might be able to work on every plant type. It is very dependent, of course, of the stadium of growth the plants are already in, because when the plants are very small, we might be still able to drive over them with our robot. But later in the process, when the plants are already grown very high, it's difficult to, up to not possible anymore, to drive onto the field without damaging the crops. It also may depend on various other factors, like the time of the day, if the animals are still on the grassland or in the stable, if there are humans around, if the traffic on the public road is perhaps come to a halt because we were able to set a gate at some point. And all of those things make up for a context the robot has to drive in. So this is mainly about navigation in the first place, but we also think a lot about behavior, like maximum speed, which control algorithm and which navigation algorithm to use, and perhaps if it is necessary to turn on a warning signal on the robot. For more specifically, for those contexts, we define different ROS algorithms and parameter sets for those algorithms we want the robot to use. And on these zones, we model waypoints on the intersection of those zones as a topological connected graph to be able to drive from one zone to the other and to handle the switch between two different contexts. So at this point, we have the zones. We have, you can see in the graphic, the labels stand for the zone names and the parameters of the zone, or at least exemplary. And now you can see the graph where the blue dots are the waypoints in the intersection of those zones, which mean that whenever a robot wants to cross from one zone to the other, it has to cross a waypoint, and at this waypoint is the context switch is handled, and new algorithms are set and new parameters are set for the robot and for the next segment of the path. So if we want to accomplish a very simple task, or so it may seem, to drive from A to B, so you can see point A and point B given in the map. The path is decomposed along the topological layer into subsegments from one waypoint to another, and at each waypoint a new movement command is given to the robot, along with new algorithms to use, maybe a new map representation in the future, and a different parameter set to operate in the new context to drive in. So on an abstract layer, you can see here very simple web GUI we implemented for testing based on Google Maps. So we see our robot at some point localized with GNSS, and we want to drive it very abstractly, for example, to the courtyard of the farm and then back to the field. And internally, the path is then decomposed along the topological layer by adding the starting and the end point to the graph temporarily, doing a Dijkstra's or a star search, and then traverse the topological graph in the real world using parameters which are defined by the zones we modeled in the beginning. We use for that MoveBase, the main technology we built on here is MoveBase Flex. Some of you may already know it's been published by Pütz et al. Some years ago, and it's essentially a more flexible, more adaptable version of the classic MoveBase technology, where we can, for each movement command, also define the navigation algorithms and new parameters, and do not have to instantiate the whole software stack anew every time for that. So internally, we have three components. We have the waypoint server, which serves as a provider for our topological graph. We modeled manually beforehand. We have the path decomposition, where a goal from A to B is provided, for example, by the user or by a robotic planning algorithm, and then decomposed along the waypoints of the topological layer, and then fed one subsegment at a time to MoveBase Flex to be able to drive to the next subsegment. Yeah, in ROS, in ARVIS visualization, this looks like this. What we can see here are the modeled zones in a transparent layer. And in blue, we see the waypoint graph we modeled for our test site. So I think I have to can jump back here. So you see here, this is our test site, our farm, which is, by the way, not in simulation, but we really had this visualization come from the live experiment at this farm. And here we see the internal representation the robot got globally with the topological layer for each zone. And to summarize, you can say each edge in the graph is in exactly one zone. So each subsegment of the path, the global path, will cross exactly one zone, and thus can be mapped to one set of parameters and one planning algorithm. Okay, I will show you the video now. And
so what we see here in the video is our test robot Arox, which drives on our test site in the north of Germany, in Lower Saxony, Niedersachsen. We see how it got the command to drive from its default environment near the supply container to a point on the courtyard of the farm. And we see it here driving fully autonomous without human intervention over these different contexts. So here in the sensor visualization, we show in between, you can see how the Arox perceives its environment and even is able to navigate around obstacles we did not anticipate when we started the navigation. So what is essentially shown is the combination of the different layers of navigation, the top level topological layer, where we can integrate various different and very heterogeneous areas on which the robot should navigate, and the typical two-layered navigation below of that. Many of you may know from typical robot navigation, that is a global or static occupancy map and a more dynamic local obstacle map, where obstacles or dynamic obstacles are added at runtime and then forgotten quite immediately after. Yeah, this is a test drive we did at the end of August. So the corn is quite high. Of course, by now it looks a bit different.
Okay. Yeah. So we saw what it already can do and how it is already able to integrate the different navigation software stacks available in the ROS community. But of course, there's further work and future work as this talk is already called towards context-aware navigation. So we are far from final here. What we already can do is to drive within the similar representation. You saw the occupancy grid navigation, which is quite typical for a lot of robot applications. But of course, we want to be able to also accommodate for more complex areas and countrysides than the one in northern Germany. So what we want to do is to extend move-based flags further, not to only be able to change online between different navigation algorithms, but also between different planning representations. Most navigation is done on 2D occupancy maps or some variations of that. And we want to also include our previous works and related works in 3D mesh navigation into that, and also be able to switch between between different custom controllers necessary, for example, for driving in rows on the field, in planned rows on the field, or for driving in stables and things like that. Also, I showed you how we generate the zones, or how we model the zones on the farm, and we want further expand that to work more autonomically. But most important, we decided to not call this technology already semantic navigation or semantic mapping, because what we do is we have a quite straightforward mapping between a zone and a predefined set of navigation software and parameters. But what we really want to do, because we think it will be necessary to really achieve autonomous functions, is that we need semantics to be able to infer those parameters instead of just looking them up. So what we're currently working on in this case is that we want to expand the representation of the farm, in that we are not using given or predefined sets of software stack and parameters anymore, but only give qualities of the surroundings, of the context, and then have a rule engine logically infer the resulting use of technology and parameters. Also, we want to expand the behavior, which is controlled by the system. So at the moment, it's mostly about movement, because naturally comes very natural with navigation, comes things like movement speed, acceleration, and stuff like that. We want to expand that for more sophisticated behavior, like, for example, on public roads, we want to drive on the right side as far as possible. When in areas where humans might also be, we want to avoid unpredictable movements as not to startle anyone, and especially in crowded areas, or for example at night, we need to switch on warning signals or warning lamps automatically. So essentially, we want to go from context awareness to really understanding the semantics of the surroundings of the robot. Yeah, in conclusion, what we already have is the integration of multiple heterogeneous contexts, which is from our point of view, required to achieve real autonomic systems. We have added the topological layer on top of the typical two-layer navigation and localization architecture of common ROS architectures. And we already showed that we can use more flexible frameworks to include and to integrate different state-of-the-art software stacks available in the ROS community to achieve a more comprehensive approach to driving on a real farm, which normally consists of very heterogeneous environments. Thank you very much. That's it. Last but not least, I want to thank, of course, our sponsors, grant givers. I'm sorry, I'm missing the word here.
Thank you very much, Benjamin, for your presentation. Do not hesitate to ask some questions in the tab, foreseen for that. I have one question, in fact, for the moment. The parameters of control and the kind of control you are applied or perception algorithm is defined by user. And so you expect to make the robot decide by itself of these parameters, right?
Yeah.
And
right.
How do you expect to manage that? Do you want to use learning approaches?
So at the moment we use a rule-based system. It's a technology we develop on our own. It's called Semper. But I think it's not published yet, so I have no reference to give you. But it's essentially a system where we use a RETI network to work with facts and rules, and from that infer with forward reasoning new knowledge on new facts. So it's essentially a rule or fact engine. And so what we are doing right now, currently working on, is defining rules so that from a still very reduced model, of course, of the environment and of the parameters, we can infer from qualities of the surroundings to technological implications. So our idea is that in the future, maybe we can work with a farmer to have attributes like how crowded is the space? Are there animals to be expected? Are the animals easily startled? Is there expected to be machinery around or people driving machinery, workers essentially? How is the surface of the ground? Is it sealed like pavement or asphalt, or is it open like gravel, soil, or grass? And from that attributes, we can, for example, derive that the best or my favorite example is that at the moment we are trying to incorporate a weather station nearby so that we can see like when it rained for 2 days, we expect the grass to be slippery. And we expect, or if the sun shined for more than a week in a row and it's very dry, we expect the soil to be slippery because it's very dusty or gets very dusty at the side. And of course, those parameters have also to be checked with experts because we are, or most of us have some experience working on agricultural sites by now, but we are no farming experts, but roboticists. But nonetheless, many of those attributes can be transferred to other farms because soil is, when soil gets dusty, it gets slippery most of the time, not really depending on where you are. Yeah, exactly.
Okay, I'm sorry, the time is running out. Just before leaving, you mentioned that you are using ROS behaviors for robotics control. So are you using also ROS2? And if possible, did your algorithm, management algorithm, is open and can we download it from ROS?
Two questions to answer. Yeah. We did not use ROS2 yet. We evaluate, in our group, we kind of evaluate the state of ROS2 every 6 months or so to see if it's already possible for us to switch. But up until now, we were not able to do so because too many immature technology stacks or too many missing pieces. We are looking forward to switch to ROS2 as soon as possible. We are a research institute, so we are very open to new development at that point. But of course, as we do not build our systems on our own, especially, but rely on board, but not really the shelf because it's mostly configured to our needs. But nonetheless, we buy our robotic platforms or the hardware for that. And there we, of course, we heavily rely on available drivers and so on to work with that. And most of those are unfortunately still not available with ROS2. The second question, the framework Move-Based Flex I mentioned is already public available. It's like I said, it's been published by Pitts et al. And is available as software on GitHub. The software we integrated here is not released yet. We plan to do that, but it's not in a state where we dared to publicly release it. But if you're interested, please get in touch, and of course we can show you and perhaps even give you access.
Perfect. Thank you very much. So time is running out. So there is the remaining questions that you are able to answer in the tab. If it's not the case, you can ask any questions and find the email of all speakers on the RobAgri booth or INRAE booth, and so you are able to keep in touch with the speakers. So I would like to thank you all the speakers for their interesting presentations and diverse presentations. I would like to thank you also, organizer of FIRA, to welcome the second scientific workshop of RobAgri and INRAE. You can see on our booth if you want some more details about the organizations. And finally, I would like also to thank the audience for their kind attention and their interesting questions. So it is the end of the questions. We have a third session tomorrow at the beginning of the afternoon, devoted to the relationship between activations of implements in coordination with robots in order to achieve actual agricultural tasks. So thank you very much, and see you tomorrow.